What makes quantum Fourier transform so efficient with few gates? Imagine trying to solve a puzzle that normally takes hours, but with a special trick, you finish it in minutes. That's what the quantum Fourier transform does in the world of quantum computing. It transforms complex quantum states into a form that makes many problems easier to solve. But what makes it so quick and efficient, especially when using only a small number of quantum gates? Let's break it down. First, the magic lies in how the quantum Fourier transform breaks down the transformation into simple steps. Instead of working on huge data sets like classical Fourier transforms, it uses the structure of quantum states. Quantum states are built from tiny units called qubits, and their combined state can be written as a tensor product. This means the entire transformation can be built from operations on individual qubits and pairs of qubits, which are much easier to handle. Next, the core tools used are the Hadamard gate and controlled phase rotation gates. The Hadamard gate puts each qubit into a superposition, creating many possibilities at once. Then, the controlled phase rotation gates apply precise phase shifts based on the positions of the qubits. These phase shifts encode the Fourier information efficiently. Instead of needing a huge number of gates, the total controlled rotations grow only quadratically with the number of qubits, roughly on the order of the number of qubits times itself. This keeps the circuit manageable. Another reason for its efficiency is that in practical setups, small phase rotations can be ignored or approximated without losing much accuracy. This reduces the total number of gates needed. Also, some controlled phase gates can be combined or simplified using known identities, cutting down the circuit depth even further. This is especially useful because quantum hardware has limits on how many gates can be applied before errors creep in. Speaking of hardware, the quantum Fourier transform circuit can be designed so that the number of sequential gate layers grows only linearly with the number of qubits. This means it can be executed quickly, reducing the chances of errors from decoherence. The final step involves swapping qubits to reverse their order, which only takes a few swap gates and adds very little overhead. This efficiency makes the quantum Fourier transform a key part of many quantum algorithms, like Shor's factoring algorithm and quantum phase estimation. These algorithms relying on transforming phase information into measurable data, and doing this with fewer gates saves time and reduces errors. That's why the quantum Fourier transform is so powerful and central to the promise of quantum computing. Its clever design, polynomial scaling, and compatibility with hardware constraints make it a true workhorse in the quantum world.